Hello, welcome back to A Slice of Physics. We have recently been talking about charge flow as it relates to charging up capacitors, etc. And today we're going to define the concept of electric current as it relates to charge flow. We'll start with looking at what happens when you have an electric potential difference across the wire. And one of the things that happens is that there's an electric field created inside the wire, which is a conductor. We'll then see how this electric field or potential difference facilitates the flow of charges in the wire, which leads us to the definition of current as the flow of positive charges, and we will touch upon the conflict this has with the microscopic model. Finally, we will see how electric current is defined as the rate of flow of charges, look at the equations that correspond to that, and close with the unit of electric current, which is amperes. Since none of us have seen charges actually flowing with our own eyes, it's a little hard to visualize, so I will start with using the example of water and use the gravitational analogies to introduce the concepts of charge flow and current. So let's say we have two reservoirs of water over here. One is higher than the other. Well, you know that the higher you get, the more potential energy you have. So the water in this top reservoir has a higher potential energy as compared to the water in the lower reservoir. Now, while we understand potential energies like this in the gravitational context, we generally don't talk about gravitational potential. But even in the gravitational sense, it is true that this higher reservoir is at a higher potential than the lower reservoir. So U is for potential energy and V is for potential using our standard symbols. So when you have a terrain like this with a hill on Earth, the higher points are at higher gravitational potential and the lower points are at lower gravitational potential. And if you introduce an object over here, that object would then have a higher potential energy at the higher spot and a lower potential energy at the lower spot. So I've got a pipe connecting these two reservoirs, but it's closed. What would happen if I opened it? So now I've opened this pipe, and you know that the water will flow from high to low. So I will have water leaving the top reservoir and adding more to the bottom reservoir. So the observation here, and these would be useful as we get to our electrical analogy, is that water flows spontaneously from high potential or high V to low potential or low V. But once it's at the bottom reservoir, it's happy being there. It's not going to go back to the top reservoir. But we can change that situation. We could connect this bottom reservoir through a pipe to a pump, which would move the water from low potential to high potential. It'll move the water in the opposite direction of what it normally wants to do. So if I turn this pump on, I can pull water from the lower reservoir and dump it into the higher reservoir. So just to be clear, the flow of water here from high to low potential happens spontaneously, but this flow over here from low to high potential required a pump to move it. So the pump did work on the water to increase its potential energy. So if I have this situation, I could have a continuous flow of water from the high to the low and then being pumped back up to the high, and you've seen this setup in many places, in a backyard waterfall, for example, and in many other water features. So let's, with all this in mind, see what happens in an electric circuit. So let's say I have a battery over here, and you know from previous discussions that the battery has a positive end and a negative end, and we show the positive end with this stub. And the purpose of the battery was to maintain a potential difference across its ends. So there is a potential difference, which means the potential here is high at the positive end and the potential here is low. This is not gravitational potential, this is electric potential, and what we had here in the water situation was gravitational potential. So if I now connect a wire from the positive end to the negative end like this, what would happen? Well, if we were to continue with the water analogy, charges in this case would flow from the high potential to low potential. So we would have a spontaneous flow of charges from high V to low V. So you'd have charges moving this way. And then once they get to the lower potential, they're happy sitting there, but the battery works like a charge pump, and it pumps it up to the other end to keep that flow going. So this is what creates the flow of charges or current. So a couple of things to note. We have a wire, and the wire has a potential difference across its two ends. One end is at a higher potential, the other end is at a lower potential. You know that when you have a potential difference, you also have an electric field. So you would have an electric field inside this wire that points from high potential to low potential, like that. Now you may be a little surprised when I say that there's electric field inside the wire, because the wire, after all, is a conductor. And you remember from our early discussions in this course that conductors don't have any electric fields inside them because the charges are free to move around to neutralize any field that has been placed in it. But that was in a situation where the conductor was in electrostatic equilibrium. Here, the situation is no longer electrostatic equilibrium. When you maintain an active potential difference across the ends of a conductor, it's no longer in equilibrium, so it will have an electric field inside it. So it's this electric potential difference which creates the electric field inside the wire, which then is responsible for the spontaneous flow of charges from high potential to low potential, or along the direction of the electric field. And then inside the battery, it'll go from low potential to high potential as the battery does work on these charges, just like the pump did work on the water to move it from low potential to high potential. So charges at the positive end would have a higher potential and also a higher potential energy, and charges at the negative end have a lower potential and also a lower potential energy. So this is how the model of current was developed. But you might be thinking about another conflict that's going on in your mind as I have discussed this. You know that the charges that are free to move are the negative charges, they're electrons. So that flow would be completely opposite everything I have shown here. When I make this connection, the electrons will shoot out of the negative end of the battery, move in the wire in the opposite direction of what I showed, and go to the positive end. And then the battery would actually do work to push those electrons back to the negative end. So because electrons are negatively charged, when they sit at the lower potential, their potential energy in fact is high over here and low over there, which is what facilitates their flow that way. Now this conflict may be an issue for you to wrestle with at this point in time, but we are saddled with this because of when we discovered what? We had worked with circuits and currents and batteries and potential differences a long time before electrons were discovered and the microscopic structure of the atom was understood. And when we studied this, we related that to our experience with water, and we kind of defined everything as things that would go from high potential to low potential and defined current that way. Once we figured out the microscopic model of the atoms, we realized that in reality it happens the opposite way. But thankfully, we don't care. I mean, that level of detail about what happens inside these wires, no one has seen charges move. So we can happily pretend that positive charges are what are moving in these wires, and they move from high potential to low potential. They move along the electric field. And so all of that works fine. And we will stick with that for our definition of current. So electric current has always been and will continue to be defined as the flow of positive charges. And mathematically, current, which is written as I, so let me show that over here as well, is defined as the amount of charge flow, delta Q, divided by the time it takes for that charge to flow through one point in the circuit, delta T. So it's the time rate of charge flow. So for example, if I have the amount of charge that flows through a point in the circuit of 90 coulomb in a time period of 60 seconds or 1 minute, then my current would be delta Q over delta T, which in this case would be 90 divided by 60. Units would be coulomb divided by second, and that gives me 1.5 coulomb divided by second. Now the unit of current is coulomb divided by second, but it's given a different name. We call it ampere, and it's written as uppercase A and 1 ampere is simply the same as 1 coulomb over second. So to summarize, in this slice of physics we saw what happens when you maintain a potential difference across a wire. Well, that situation creates an electric field in the wire, which is okay because it's no longer in electrostatic equilibrium, and this electric field or potential difference facilitates the flow of charge, which is what electric current is. Electric current is defined as the flow of positive charges, notwithstanding the conflict with the real world of what happens inside the wires with electrons moving. We can ignore that safely and go with this definition for the rest of this course. And given that definition, electric current will go from high potential to low potential, just like water does, and it goes in the direction of electric field. Mathematically, current is defined as the time rate of charge flow, and so the units would be coulomb per second, which is given the name ampere, written as uppercase A, and by the way, the symbol for current is the uppercase I. Thanks for watching. See you later.